Hello and welcome back to our Docker series. Today we'll be discussing the most, let's say, requested topic on our channel, and that is Docker networks, which of course plays a crucial role in connecting Docker containers and enabling communication between them and the outside world. Docker networks are essentially virtual networks that allow containers to communicate with each other and other services, regardless of which host they're running on. By creating and working with Docker networks, you can configure and manage the connectivity between containers and external systems. With that said, let's dive in and explore the world of Docker networks. First off, let's talk about Docker network drives. Docker provides several network drivers, each designed for specific use cases. Some Docker network drivers come as a default option when you install Docker. These default drivers are commonly used and readily available for creating and managing containers. So if you run Docker Network ls on your terminal now, you'll be able to see the most common types. So in here, we have network ID, name, type of the drivers, and the scope. And in here, by default, we can see that Docker is listing three driver types. The first one is bridge, the second is host, and the third one is null. So let's break this down even further. This is the default driver or network type used when you create a container without specifying a network. It creates an internal network on the host, allowing containers to communicate with each other. This means that any container created with the bridge network will share the same IP range and be able to communicate with other containers on the same network without any additional configuration. The bridge network driver is an essential tool for containerized applications that require internal communication between different components or services running on separate containers. It comes pre-installed with Docker and is widely used for basic container networking. Okay, let's do a demo of a bridge network type. So we will start by creating three containers using the docker run command. So for example, let's be creative and use some, let's say, Star Wars geeky names for this. So we'll start by running docker run, and then let's do itd, and we will also specify a name, let's say galactic bin. And we'll choose a Docker image called nginx alpine. So we'll give it a moment or two to actually find the image and pull it down locally onto our machine. And if we do Docker images, we'll be able to see the newly pulled image here on our machine. We'll do the same for the other two images. So let's do docker run the container. We'll also specify remove to actually execute the container once it's been completed. We'll give it a name Jedi jar, and then we will use busybox for this example. Once again, it will take a moment or two to pull down the image, and let's do docker images, and we'll be able to see our busybox here as well. And last but not least, docker run itd, and then we'll specify a name Mandalorian box. And for this one, we'll use Python Alpine image. Oh, that's a typo. Once again, pulling down the Python image. And let's double check that's all correct. As you can see here, when you create a container without explicitly specifying a network, Docker automatically assigns it to the default bridge network. So if we do, once again, Docker network ls, Docker network ls, so it will be, of course, creating the container in the default, obviously assigning to the default bridge network. The default bridge network itself is a virtual network created by Docker on the host machine, in this case on our laptop, while the default bridge network provides convenient isolation and connectivity for containers. It may not always be suitable for production environments, of course, with more complex, let's say, networking requirements. So in such cases, users, of course, can create custom networks with their own specific configurations to really meet their needs, and such as, let's say, connecting containers to an existing network or completely isolating containers within a custom network. So with that being said, we can also do Docker network ls, and we can grab the ID of the bridge network, and we can also do Docker network inspect, and then we'll paste the actual ID in there. And if you scroll up, you will be able to see our containers that we've just created. And as we mentioned previously, they have been assigned automatically to the default bridge network, which also we can see the driver, of course, has been defined as bridge, and our containers Jedi jar, Mandalorian box, and Galactic bin. Now, let's continue by listing our containers and networks. So if we do Docker PS, we'll be able to see 3 container IDs for each one of the containers, their images. We can also see their creation times and, of course, their names. We did just go through the network inspect command, which is really, really useful, of course, also to keep notes of in the future. With this command, you will be able to get all the detailed information, which will include details such as we've previously seen, containers, name, let's say endpoint ID, MAC address, IP address, and so on. Now let's access one of the containers using the docker exec command with the sh in the end. So let's do docker exec, and we'll pick, let's say, the top one, and do sh. And once we're inside the container, we'll use the ipadd command to view the network interfaces and their IP addresses. So if I do that, you'll be able to see all of that listed in here. And finally, let's test the actual connectivity. So we'll try to ping one of the other containers. So if we scroll up to when we ran docker network inspect command in here, we can see all the listed IP addresses. As we mentioned previously, this is a pretty handy command to have in place to really easily access all the information that you need, such as the IP address, to be able to check the actual connectivity. So considering we are currently in the Python Mandalorian box, we will pick either Galactic bin or Jedi jar. So let's make this simple for us, and we will just run ping and then paste the IP address in here. And as you can see, we have managed to successfully ping the other container that is also on the same network as us, which is showing the successful communication between the two containers, confirming that, of course, they can reach out each other over the Docker bridge network. In a real-world example, we can probably highlight a use case such as when developing a basic web application, let's say, that's been consisted of a front end and a back end. You would like to configure Docker containers for the front end. Let's say in this case, you might be using Nginx and a back end MySQL components of the web application. You can create a Docker bridge network that, and in that case, connect the containers to this network using the -- network flag. This will ensure, of course, that the containers can communicate with each other in a secure and an efficient way. And of course, as we've seen in a previous demo, bridge network is also a default network. So even without specifying the network flag, they will still be assigned to the bridge network. And Docker itself will be responsible for routing the network traffic between containers that are on the same bridge network, which provides protection against external networks. So additionally, only containers within the network itself can communicate with each other, which guarantees a secure communication. The host network driver is another default option provided by Docker. When using this mode, containers share the same network namespace as the Docker host. This means that they can access the network interfaces of the host directly without any network isolation from Docker. In other words, containers using the host network driver mode have full access to the host's networking stack, including its IP address, port, and routing tables. This can be particularly useful in certain scenarios, but it also presents a security risk and may not be suitable for all use cases. This particular driver is useful for scenarios where, let's say, containers need maximum network performance or require access to host ports themselves. All right, so with this demo, we will start with listing all our networks. So let's do Docker network and less. And in here, as previously mentioned, by default, we will already have the host network type created for us by Docker. And for this exercise, we will use the Ubuntu image. So we'll create a new Ubuntu container with a type, network type set to host. So we'll do Docker run itd, and then we'll do rm network host, and then we'll use an Ubuntu image, let's say 14.04, and let's put bash in the end to exec straight onto the container itself, and we'll just give it a couple of moments to complete. And if we do docker ps, we can see the container up and running. So if we just do docker exec it and copy the container ID and here and do sh, and we'll use ifconfig command to go through all the network interfaces that are currently running or created on our Docker container. And if we open another terminal, we can then also do that on our local machine as well, and then we can do a comparison to see that the actual network configuration is pretty much mirrored from our local machine or the host itself onto the container that we've just created. So I just close that for now, and we will clear up the screen and exit the container. So when containers are set up with the same network configurations as the host, they can be accessed through the port on the host's IP address, because once again, all the configuration has been mirrored and used as well in the Docker container itself. So for instance, if you launch a container that uses support 80 and you enable host networking, as we did just now, the application itself running inside the container can be accessed through the port number 80 on the IP address of your local host. So let's move into further demos. So we'll do Docker PS. And we'll grep the container ID once again, and we'll do Docker container inspect, and we'll paste the ID in here. And as you can see, the network ID itself in this scenario is the same as the host ID from our local machine, and the IP address is currently set to null. So as you can see, the value is empty, which means that you can easily, of course, access the application using the host machine IP address without port mapping. And the host mode networking is particularly useful when you want to optimize performance and avoid any sort of port mappings. So it is important to note that host networks cannot be duplicated, meaning that if you do want to create another containers using, let's say, a host network, you can't have two running at the same time. So if you do have one already present, please make sure that, of course, you delete it before creating a new one. So let's do another demo. Let's say Docker network create. And then we'll use again host network type, and we'll just do a test net. And as you can see, the error here, response from daemon, only one instance of host network is allowed by Docker. So once again, if you want to create another host network, please make sure that the existing one is deleted first, and then create a new one with the name, the network type set to host. In the real world use case scenarios, we can probably imagine an old application that needs to connect to, let's say, a specific port on the host machine. You can use that host network driver to put it inside the Docker container. This way, the application can have unrestricted access to the host network resources while, of course, staying safe. This is especially useful for applications that need to connect to, let's say, low-level network interfaces. The non-network driver is also included as a default option. The non-driver is a type of container networking that completely disables all networking for the container. This is particularly useful in scenarios where complete isolation of a container is required. So when the non-driver is used, the container will not have access to any network interface, including loopback interfaces as well. It's important to note that this driver should not only be used in situations where the container does not require any external connectivity, as it will not be able to communicate with the host or any other network. All right, before we jump into our second demo, please make sure that you've cleared up all the previously created containers, just so we can prevent any potential interference. And if you look at the Docker images, we did save the previously pulled one down just in case we do need to reuse them again in the future to also save up some time. So without further ado, let's run a busybox container with non-driver assigned to it using the following commands. So docker run itd, and in here you'll also be able to see our already auto-populated commands. So we'll be using the network none with the name droid -box, and for this particular example we will use our previously pulled busybox. And if we do docker ps, we'll be able to see our Docker container up and running. And let's exec onto this container, also copy the container ID, and also use sh to run IP add. And in here, we're particularly looking for a tunnel being assigned to none, as well as the IP6 tunnel also being assigned to none. So the output is really important because it's displaying you information about all the network interfaces. And in this particular example, we can see that it only has the loopback interface and two other interfaces. So the loopback one is here, the top one, and also we've got tunnel 0 at none, and also IP6 tunnel at none, which are related to tunneling but not currently active because the container is not connected to any network. So overall, this demonstration illustrates how to use a Docker container without network access and inspect its network configuration. In a real-world scenario, when you do need to make sure that a container can't connect to any network at all, you can use the non-network driver in that case. This is particularly useful for, let's say, sensitive environments where you're running an application that deals with sensitive data or runs some sort of untrusted code. And by isolating the container from the network, you can also reduce the risk of unauthorized access or potential data breaches. When working with Docker Swarm mode, the overlay driver plays a crucial role in facilitating communication between containers that are deployed across multiple Docker hosts. The overlay driver creates an overlay network that spans across the entire Swarm cluster, allowing containers to communicate with each other seamlessly and efficiently. This network is essentially a virtual network that sits on top of the physical network infrastructure and provides a secure and isolated environment for container-to-container communication. By leveraging the overlay driver, you can easily deploy and manage distributed applications that are composed of multiple containers running on different hosts without worrying about network connectivity issues or potentially complex configuration settings. In a real-world case, let's say you're working on a distributed app using Docker Swarm, you might have multiple services running on various Docker hosts. To be able to allow them to communicate easily, you can use the overlay network driver to create a virtual network that spans all the nodes in the Swarm. This lets the containers communicate with each other no matter where they are physically located. We will not go through a demo session on overlay network type in this particular video. However, we will be covering Docker Swarm in one of our upcoming videos, so please do stay tuned. The MacVLAN driver is a powerful tool that helps assign a unique MAC address to each container, making it appear as a physical device on the network. By doing so, it allows containers to have direct access to the network, which is particularly useful when running network services. This driver is commonly used in scenarios where there is a need for multiple containers to interact directly with the network without having to go through NAT or other network address translation mechanisms. By assigning a unique MAC address to each container, the MacVLAN driver makes it possible to have fine-grained control over the network interfaces of each container and enables more flexible networking configurations. In this walkthrough, we'll guide you through setting up a MacVLAN network on Docker. So firstly, we will start by determining our subnet. So on macOS, if you go to your terminal, you can type ifconfig to get the network configuration displayed on your local machine in order to determine all the active network interfaces on your Mac. We will be specifically looking for either N0 or N1 on macOS, followed by INET and the IP address. Also, this will help us determine the actual subnet, so what sort of subnet it corresponds to. So in this case, it'll be 192.168.10.24. All right, so we don't have any containers running at the moment. We will carry on with creating a new MacVLAN network. So we'll do Docker network create, and then -d MacVLAN. We will specify the subnet that we've just determined. So 192.168.10 and /24. We'll also put gateway in here, which will be 168.1.1. We'll specify the parent interface, which will be ETH0. And lastly, we'll give it a name. So let's do headintheclouds MacVLAN Network. Super. So after the creation, let's verify the network, running network ls command. And in here, we can see the newly created network. Also here under driver, we can now see also MacVLAN being displayed. Now that the network is created, let's run a container that will be connected to the newly created MacVLAN network. And lastly, we will assign the IP address to our container. Here, make sure to specify an IP address that is not within your DHCP IP range in order to avoid any potential IP conflicts. So we'll run docker run remove itd, and then we'll give it a name, head in the cloud MacVLAN. Let's say call it test, and then we'll specify the network. So we can just copy it from here, and let's give it an IP address. So we can do 192.168 following the subnet, and then let's do 111 just as an example. We'll use the Docker image Alpine, and we'll also run bin sh. Super. And let's make sure that the actual container is running. So Docker ps, in here we can see our test container successfully executed and running. We can also see a little more details, let's say, about the container itself using the docker inspect command. So if you do docker container inspect and then copy the ID, here under networks, we will be able to see the headintheclouds MacVLAN network being assigned to the container, and also the IP address that we've specified previously to this container. We can also see the MAC address being assigned, which is exactly what we wanted, the gateway, and so on. Now let's create a second container as follows. So in this case, the container will automatically be assigned an IP address by the Docker itself, so we don't have to specify it. Let's clear this up and we'll run docker run rm itd. Let's say a name, it can be head in the cloud MacVLan test 02, and we'll give it a name of our MacVLan Network, and we'll use the Alpine latest image with bin sh in the end. Did I? Yes, I did. Make a typo in here. Super. Do docker ps. We can see also our newly created container a second ago, test 02. And next we'll continue with trying and establishing if the containers actually can ping each other. In this case, we are basically testing connectivity of the first container from the second container. We can do this using a single command as follows. So docker network ls, and let's grab the the ID of the MacVLAN network. So let's do docker network inspect this ID. We'll just keep it here because we would like to have obviously visibility on the IP addresses for both containers for the testing purposes. We can also do docker ps to get the IDs of our Docker containers, and we will do docker exec it on the let's say we'll grab this container ID in here, and we'll do a ping command to the second container, which will in this case be test 2. And if we scroll back up under our containers from the network inspect, we can also grab the IP address from here, and if I paste it in there, we can see, of course, the successful ping from one container, so from our test, the first container we've created to the second one. We could also do another test by directly accessing the let's say container number 1, and let's do bin sh. And if I do ping, I can also copy the IP address of the second container. We can also confirm that we can do this directly from the container itself as well. If you try running the same container from the other same command, from the other container, you'll notice that both containers are able to communicate with each other. Really, really important here to note is that the Docker host, so our local machine itself, cannot communicate with either of those two containers and vice versa. So attempting to do so to ping the host from the container and vice versa, it will reveal that the communication between the two is not possible. So let's see also that in action. We'll make sure now that we exit the container, and we'll try to ping the IP address. Let's say if we scroll back up, we'll pick the IP of the first container that we've created, and we'll try to ping it from our local machine. And if we oh, sorry, I'm still in the container exit, and then ping from our local machine. As you can see in here, from the container itself, we were able to establish a key communication connection between the two containers. However, if I do try to do this from my local machine, it is actually timing out. To also demonstrate this from the container onto the local host, let's just grab the actual local IP address of my machine, and we can exec again onto one of the containers, and we will also try to ping. We'll copy again the IP address from our local machine, and once again we are able to demonstrate that obviously the actual request is also timing out when trying to ping from the container itself onto our local host. So for the containers to communicate with the host, we need to create a MacVLAN interface on the Docker host and configure routing to the MacVLAN interface. In a real-world scenario, we could probably think about a situation where you would be using Docker container to host virtual network appliances, such as firewalls or routers. You can easily assign each container a unique MAC address and IP on the physical network. This will make the containers behave like separate physical devices, allowing them to interact directly with other devices on the network. And this is helpful for network virtualization tasks. So you can use the MacVLAN Network driver for this purpose. Docker comes with built-in network drivers like Bridge, Host, and None, ready to use without additional setup. However, drivers like Overlay and MacVLAN may need extra configuration, especially in complex setups or Docker Swarm. For advanced networking, custom third-party plugins can be installed, offering specialized capabilities for specific needs. Depending on your requirements, you can use built-in drivers or install custom ones to tailor networking solutions accordingly. MacVLAN and IPvlan are two virtual network interfaces in Docker with distinct advantages. MacVLAN assigns unique MAC addresses to each container, useful for scenarios requiring multiple MAC addresses on a single host. However, older switches may struggle with this, causing, let's say, performance issues. IPvlan, on the other hand, allows multiple containers to share a single MAC address, improving its efficiency, especially in cloud environments. Both have their strengths and can be tailored to specific needs, with MacVLAN being versatile and IPvlan offering enhanced isolation and IP address efficiency. IPvlan can work in two modes: L2 or layer 2 mode and L3 or layer 3 mode. In IPvlan's layer 2 mode, the default configuration operates similarly to MacVLAN bridge mode, but without assigning unique MAC addresses to containers. Instead, the Docker host acts as a switch between the host's parent interface and virtual network interface cards, or known as NICs, for each container. Communication relies on MAC addresses, facilitating the inter-container communication within the same IPvlan network. However, this setup generates numerous address resolution protocol, or known as ARP broadcasts, potentially ending up as an impact on the network performance. All right, so in this demo, the parent interface is going to be used, which means we'll use the network from the host's interface as the subnet configuration, part of our Docker network creation. The container will be attached to the same network as the host interface, and this will be set via the parent option, which will just show that to you shortly. So let's create the IPvlan network now with a container running attached to it. So as you can see here, we have just our default networks listed, ready to create the new one. So Docker network create -d, and then let's specify the network type. We will also use, let's just go back to this example as we've already done this on this local machine. The subnet itself is going to be set to 192.168.1.0, and the gateway is using the 192.168.1.1 IP address. The IPvlan mode is set to layer 2. We're assigning the parent option here, and we're just giving it a name, headintheclouds layer 2 IPvlan network. And then if we do network list, we'll be able to see that newly created network in our list. We'll also run a container. So let's just specify the network we've just created now, and we'll use the Alpine image for this demo. Something really important to note here is that the containers that we just create now cannot ping the underlying host interfaces, as they're intentionally filtered by this IPvlan network. And to be able to demonstrate that, let's just open quickly another terminal window and grab our IP address from our local machine. And let's go back into our container. We can do ping from the container onto our local host. As you can see here, it is timing out. So that's also something really important to note. If the gateway option is not specified, so in here we did give it an IP address, but in case you don't do that as part of the creation, the first available IP address in the network will be used as the gateway for the container. And if you would like to obviously check through more of that network configuration, you could also do Docker inspect using a container ID and grep for gateway to see that as well as part of the creation. So you might want to create the network without, let's say, specifying the gateway itself, and then see also what happens in that scenario. Lastly, it's worth noting that the default mode for IPvlan is layer 2. So if you do leave the IPvlan mode set to unspecified, the default mode layer 2 will be used. So we could also, if we just exit this container and do network ls, we could do the network inspect, and let's get that name of the network, and then we also grep for IPvlan mode. And in here, of course, you can see the layer 2 because we previously specified it. But again, for the demo purposes, feel free to also experiment and see what happens if you don't specify it as part of the network creation. So to better understand how this mode interacts with other hosts, we would like to go through another example to show the same layer 2 segmentation between two Docker hosts that applies to, and also the IPvlan layer 2 mode. So in this case, we will make sure to remove any previously created network, just to make sure that there's no sort of clashes. And we'll create a new network, also using IPvlan with the subnets set to, I think it's already pre-saved in our example here, 192.168.1.0, with the parent option set to this, and also we've just given another name to this network, which will be headintheclouds layer 2 IPvlan net 2. And if we do docker network ls and docker network inspect this network here. We will also we could also either grep or just run through the network configuration to see if there's the gateway IP address listed in here or the IPvlan mode. By the first look, we can't see that in the network configuration, which indicates that if no gateway IP address is explicitly specified during the network creation. So if we just refer back to the command we've just run, and here Docker automatically assigns the first available IP address, as we mentioned previously, from the subnet range as the gateway IP address. And this is also calculated based on the subnet range. So for example, if your subnet is also 192.168.10.24, the gateway IP address will typically be 192.168.1.1. And also for the IPvlan mode, if it's not explicitly specified during the network creation, the default mode, which is layer 2, is being applied. So as you can see from the command itself, and here we haven't specified it, but it is using the default option. So given this information, you can assume that the gateway IP address is likely 192.168.1.1 and that the IPvlan mode is layer 2 for the headintheclouds layer 2 IPvlan Network 2. In Docker's IPvlan layer 3 mode, each container operates with its own MAC and IP addresses, creating a virtual network environment. The Docker hosts act as a router, enabling seamless packet routing between containers and external networks, ensuring robust isolation and communication. By confining broadcast traffic to the layer 2 subnet, IPvlan layer 3 mode optimizes network performance. However, manual configuration is required to establish communication with the IPvlan network, including setting up a static route on the gateway router. Despite this challenge, Docker's IPvlan layer 3 mode offers a powerful networking solution for containerized environments, combining efficient isolation with effective communication capabilities. To better understand layer 3 mode, let's take an example of two Docker containers connected to the same IPvlan network. Each container in this example will have its own IP address and will be able to communicate with each other via IP routing. So in contrast to IPvlan layer 2 modes, different subnets and networks can ping one another as long as they share the same parent interface. This means that the two containers can communicate with each other and with the upstream network as long as they share the same parent interface. All right, so let's create a new IPvlan network using the layer 3 mode. So we will run docker network create IPvlan, and then we'll use subnets, let's say 192.168.152.0.24. Also specify another set of subnets, let's say 10.152.0.24. But we use this parameter to specify the mode, which will be level 3. And let's give it a name, headintheclouds L3, IPvlan net, and Docker network ls. There it is, a newly created network being listed here. We will run our first Docker container that will be attached to the IPvlan network with the IP address, ensuring that obviously we're taking the one from the subnet range that we've given it initially. So we'll do Docker run. Network name will be headintheclouds, layer 3, IPvlan-net. And let's assign IP address of 192.168.152, which is the range. And let's just give it 10 ITD using Alpine bin sh. And if we do Docker PS, there's our container up and running. We'll now run the second Docker container being attached to the same IPvlan network and using the IP address of the 10.1.152 IP range. So Docker run net set to L3 IPvlan net, and we'll use the IP address of 10.1.152.10 ITD Alpine bin sh. Another Docker PS. Perfect, we've got both containers running. And let's inspect both of these containers. So I'll grab the container ID of the first one. So container inspect, paste the ID in here, and we will also grab IP version 4 and address. As you can see, this is the IP address we've given it earlier when we ran this command, and we will use the same command but with this container ID. And once again, you can see when we created the container using this subnet range of 192.168.152, it's using the corresponding IP address. Now we'll test the connectivity from 10.1 to 152 subnet range to 192.168.152 range. So we'll run another container to do that. So we'll specify the network name, and we'll assign the IP address. Let's say 192.168.152.9, and we will also put remove Alpine, and let's do ping 10. We can use this IP address actually, so paste in here. As you can see, it's been successfully pinging it from one range to another, which just shows that our dev has been successful. We can do the same for testing connectivity from 192.168.152 to 10.1.152. So we can run another container. Let's make sure we specify the name of the network, and we will use another IP address from 10.1.152, let's say .9 again. IT remove once completed, Alpine ping, and we'll do 192, or we can copy it from here. And there you go. We can see it being successfully pinged as well. So both containers are able to communicate with each other using the IP routing. And this setup demonstrates how Docker IPvlan in layer 3 mode enables containers to be connected to the same subnet using the IP addresses. The primary difference between Docker IPvlan in layer 2 mode and layer 3 mode lies in how they handle network traffic and routing. So Docker IPvlan operates at layer 2 of the OSI model in layer 2 mode. This network makes the containers appear as if they are connected directly to the parent interface. Containers that belong to the same IPvlan network can communicate with each other using MAC addresses without IP routing. To communicate with external networks or containers that are in different IPvlan networks, you may need a bridge or router. And layer 2 mode is useful when you want to have your containers appear as if they are directly connected to the physical network segmentation. IPvlan layer 3 mode operates at the layer 3 of the OSI model, which means that each container on the IPvlan network has its own IP address and functions as if they were connected to a separate subnet. Containers communicate with each other and external networks through IP routing. L3 mode provides more flexibility in routing and network segmentation, and it is a good choice for situations where you want to have containers being completely isolated in their own subnets, or when you want to be more precise, let's say, have control over routing and networking policies. Thanks for tuning in to learn about Docker networking with us today. In our next video, we will dive into continuous integration with Docker. Don't forget to subscribe and hit the notification bell to stay updated on our latest content. See you in the next video. Until then, happy learning.